Well, welcome. In this video, we're going to be looking at the inverse tangent function. Now, we've already looked at the inverse sine and the inverse cosine function, so you're going to see that there's some similarities here now with the inverse tangent function. Well, let's look at the graphs of the original tangent function. And you can see that over here on the left, where we have those blue graphs. The blue lines there represent the tangent function. If you recall, for the sine and cosine function, the sine and cosine function are always in the graph of a sine wave. The tangent function, remember, is unique, however, because it does not follow that same sine wave. Remember, there's asymptotes here for the tangent function at every odd multiple of 90 degrees, so 90 degrees, 270 degrees, 450 degrees, and the negatives of those. Or in radians, it would be the odd multiples of pi over 2. So like pi over 2, 3 pi over 2, 5 pi over 2, and so on. And if you think about that, so the tangent function, we know it is a function. It passes the vertical line test. It is a function. And remember, we have the horizontal line test to see if the inverse of that would be a function. You can see that if you ignore the red lines on there, if you just look at the blue lines on there, you can see that it fails the horizontal line test, meaning that the inverse would not be a function. And they illustrate that for us by graphing the inverse of the tangent function by the red lines there. And you can look at those red lines and you can see that they fail the vertical line test, again, illustrating that those red lines are not a function. So going back to that tangent function, which would be in this middle graph here, we would have to restrict the domain. We had to do the same thing for the sine function and the cosine function for the inverse of those to be functions. So we have to do the same thing for the tangent function. We have to restrict the tangent function so it passes the horizontal line test. So if we restrict the domain to be from negative pi over 2 to pi over 2, or from negative 90 degrees to 90 degrees, then its inverse is a function. And that's what's being shown here in the middle graph. And the inverse of that is what's above me here. The inverse of that, again, the domain and range flip. So now what would have been the domain going from negative pi over 2 to pi over 2 is now going to be the range for the inverse. The range is going to go from negative pi over 2 to pi over 2. What was the range in our original function there for the restricted domain the range goes infinitely up and down, is now going to be the domain for the inverse. So we have this important fact now for the tangent function, and that's that for the tangent function, for its inverse to be a function, we have to restrict the domain to be from negative pi over 2 to pi over 2, or from negative 90 degrees to 90 degrees. And just like the sine and cosine function, or the inverse sine and cosine function, the inverse tangent function can be read as the angle, or the number whose tangent is whatever x is. And we'll look at an example of that in a second. And another way that we could write the inverse tangent function is the arctan. Just like for the inverse sine, we had the arc sine, and for the inverse cosine, we had the arc cosine. For the inverse tangent, another way to represent it is the arctan. Now, for the sine and cosine values, we had to memorize the unit circle. And so we could have some situations where we'd have to do it without a calculator, where we'd have to find the inverse sine of square root of 3 over 2, for example. In which case you'd have to know that, well, square root of 3 over 2 is when the sine is 30 degrees. So the inverse sine of square root of 3 over 2 would be 30 degrees. I'm sorry, would be 60 degrees. Sorry, I had my cosine and sine backwards. It'd be the sine of square root of 3 over 2, or the sine of 30 degrees would be square root of 3 over 2. Sorry if I completely lost you there. But in this situation here, with dealing with the tangent, we don't have the tangent memorized for every spot on the unit circle. The one spot, though, that we have to make sure that we understand is the tangent of the angle where it would equal 1. And that's going to happen when the sine and cosine are going to be the same. And if you recall from the unit circle, where the sine and cosine is the same is at where the ones digit is going to be a 5. For example, 45 degrees is square root of 2 over 2 for both the sine and the cosine. So the tangent of that would end up being 1. Well, between negative 90 and 90 degrees, like in this example here where we're trying to find the inverse tangent of negative 1, between negative 90 and 90 degrees, that's going to happen in quadrant 4. which, if we look at that between between negative 90 and 90, that's going to be at negative 45 degrees. So the inverse tangent of negative 1 is going to be negative 45 degrees. Now, if that's all they ask for, that would be your answer. Now, obviously, they ask for our answer to be in radians, so we have to convert that by multiplying by pi over 180. Now, you got to remember that when you multiply by pi over 180, you still need to reduce this. Now, to do this without a calculator, you may not recognize that 45 goes into 180, but you might recognize that 9 goes into both of these numbers. So you could take and divide both of them by 9, so you'd get negative 5 pi in the numerator and 20 in the denominator. Now when you go to reduce this further, because we're not done yet, because I can see that there's 5 that goes into both of these numbers, now I get negative pi over 4 as my final answer. Now let's look to see how to do this on your calculator. Let's look at this next one. It says to evaluate the arctan of 2.64 in radians. Again, arctan is the same as the inverse tangent. So on your calculator, one thing that's important to understand is how to determine whether or not your calculator is in radians or degrees. So if you have the kind of TI Nspire where you have a touchpad where if you slide your finger across the touchpad, if it moves your cursor around on the screen, then what you can do is this. If you move your cursor up to the sprocket in the corner, it'll tell you if your calculator is in degrees or radians. So right now I can see my calculator is in degree mode, so I need to change that. Now, if you don't have the kind of TI Nspire that has the touchpad, if you have what's called the click pad, where you have to actually push on the buttons to move your cursor around, you will not be able to access that sprocket. I know it seems kind of silly. So what you're going to have to do is you're going to have to go to the home button and go access the settings that way, as my computer doesn't want to work for me. There we go. And so you'd go to the settings that way and be able to change your settings to be in radians. But what we want to do is we want to go to, if you have the touchpad, you don't have to go this route. If you have the touchpad, the touchpad, you can go up here, click on that sprocket, and then you can access the settings directly from there. So we can go into their general settings, and we're going to change this again to be in radians. Oops. And then just hit OK. So just change it to radians. And when you hit OK, you should go back to your calculator screen. Any day now, Mr. Calculator. Oh, there we go. Okay, so now if I drag my cursor up here, I can see that it's in radians. Okay, so now what we're going to want to do is, again, we want to take the arctan, which is the inverse tangent of 2.64, and hit enter, and you should get 1.21 as your answer. Now for the next one, it says to find the arctan of 4 in degrees. So now what we're going to have to do is we're going to have to go back up here, and we have to change this back into be degree mode. And so now if I do the arctan of 4, because that's what they asked for, we get 75.96. And again, this is in degrees. We want to make sure that we label it as so. Well, let's look now at some story problems so you can see how we can apply this. So for this one, it says a plane is flying at an altitude of 32,000 feet, which is about 6 miles, and wants to descend to an airport runway X miles away at a constant angle theta. Write an equation for theta as a function of X. Well, first we're going to draw a diagram. So let's say this is our airplane. Whoops. So there's our airplane, and here's the airport. And so our airplane is 6 miles above the ground. Now you might wonder, well, how do I know to use 6, not 32,000? If you notice, our X is in miles. We want to make sure that our units are consistent. So we want to make sure that we're using the 6 miles, not the 32,000 feet. Now, if they didn't give you the 6 miles, if they just had the 32,000 feet, we would need to convert it by dividing by 5,280. Now, here's where it gets a little bit tricky. because it says it's X miles away. Now, when it's phrased like that, the X miles is referring to the horizontal distance from the airport, not the actual distance the plane would travel, not the slant distance. So when it gives sometimes they'll say the horizontal distance is X miles, but if they don't say that, if they were to say the distance of descent, then they refer to the hypotenuse of a right triangle. But in this case, since they just say that it's going to be X miles away, it's referring to the horizontal distance. Now, we want to figure out the angle that they have to descend. Now, the angle of descension is going to be the angle that's formed if the pilot looks straight across and then looks down at the airport, which would be this angle here. That would be your angle of descent, which is the same as your angle of depression. It is not this angle. If you try to find that angle, you're going to get a really large angle, which would be wrong. We'll talk about that here in a little bit. Now, that angle is outside of the triangle that we have drawn here. So if you recall from geometry, if we have two parallel lines, which is what our side X and what this other horizontal line would be, these would be two parallel lines that are cut by a transversal. A transversal is just a line that intersects two parallel lines. The alternate interior angles are equal. So that angle of descent is the same angle that we would have down here, also called the angle of elevation. So the angle of depression and angle of elevation are going to give us our same values. So now looking at this triangle, we want to use the tangent function. So the reason why we use a tangent is the side that's 6 is across or opposite the angle. The side that's X is adjacent to the angle. So it would be the tangent equals the opposite leg, which is 6, divided by the adjacent leg, which is X. And now to solve for theta, we would take the inverse tangent of both sides. So theta would equal the inverse tangent of 6 divided by X. That would be our answer. Now to find theta to the nearest degree when X equals 30, we're just going to put 30 in for X. So it'll be theta equals the inverse tangent of 6 divided by 30. When you do that on your calculator, I'm just going to give you the answer. You would, rounding to the nearest degree, we get 11 degrees. Now, let's say if we got a really large number, like let's say if we got 79 degrees as your answer. Well, or I should say, 79 degrees as your answer. If we got 79 degrees as your answer, you would hopefully catch that would not make sense. Because if you were traveling, if you were in an airplane, and all of a sudden the airplane started to descend at an angle of 79 degrees or about 80 degrees, I think you'd start to freak out. Because 79 degrees is not the angle of descent, that's this angle here. So if you got 79 degrees as your answer, you found the wrong angle measurement. So you'd want to find, you wouldn't have to do it all over again, you just have to subtract it from 90 to be able to get the 11 degrees. You just want to make sure that your answer makes sense. Okay, let's look at the next one. I'm going to help you get this one set up and we'll do this one together. It says, Edie is watching a skyscraper being built from her apartment 0.75 miles away. Her third floor window is 28 feet off the ground. As the skyscraper reaches a height of 8 feet, what is the angle of elevation to the top of the skyscraper in terms of h? Well, if you notice here, our units for everything, except for the distance her apartment is from the skyscraper, our units are in feet. So we need to change that 0.75 miles to feet. The way that we do that is we take 0.75 times 5,280, because there's 5,280 feet in 1 mile. And this is less than 1 mile. So it's going to be less than 5,280 feet. When you multiply it by 0.75, we end up getting 3,960 feet. Okay, so let's draw our diagram. So let's say this is her apartment, and this is her skyscraper. So let's say she is at the top of that apartment building, which is a 3rd story. And if she were to look straight across at that building and then up at the top of the building, that is the angle of elevation. That is what we're going to be looking to find. And the distance between her and that skyscraper is 3,960 feet. Now this is where it gets a little bit tricky, because the height of the building is this side here. That is not what we want though for our triangle. We don't want that side. I just want to figure out what's
this side of our triangle? Well, remember, she's 28 feet above the ground, so the height from this point to the top of the building would be h minus 28. So when we go to set up our ratio here for the tangent, because this is the opposite leg, this would be the adjacent leg, it'd be the tangent of theta equals the opposite leg over the adjacent leg, which is 3,960. But they want this to be solved for theta, so we take the inverse tangent of both sides. Which would give us the inverse tangent of h minus 28 over 3,960. So in part B, when it says, what is the angle of elevation when the skyscraper reaches a height of 400 feet, we just put 400 in for h. So theta would equal the inverse tangent then of 400 minus 28 divided by 3,960, which when you do that on your calculator, you get about 5.4 degrees would be her angle of elevation. Now, I want you guys to do this one on your own, but I'll help you get the diagram set up because it's set up a little bit different, or it's worded a little bit different. It says by federal law, every new public building must have an access ramp with a slope of 1/12 or less. What is the maximum angle of elevation for a ramp? Well, the fact that it says that the slope is 1/12, you got to remember what a slope is. A slope is a ratio of the rise over the run. So in this case, the rise is going to be 1, the run is going to be 12. So when we create our ramp, the rise is going to be the height of the ramp. The run is going to be this horizontal distance down here. So that's going to be 12. So the angle of elevation is going to be this angle here. So why don't you guys take a minute to see if you can't figure out what that angle value would be, what theta would be here. So why don't you pause the video and hit play when you're ready to check your answer. Okay, so let's see how you did. You should have gotten 4.8 degrees as your answer. The way that you get that is, again, we're using the tangent function because 1 is the opposite leg, 12 is the adjacent leg. So it'll be the tangent of theta equals the 1/12 or 1/12. So we take, to solve for theta, we take the inverse tangent of both sides. So theta equals the inverse tangent of 1/12, which when you do that on your calculator, you get 4.8 degrees. Now, we're not going to take the time to do this last example. I think you have a good enough idea of how to use the inverse tangent here on these story problems. So with that, good luck now as you work on your assignment.